Значит, он, докладчик наш Anar Dosi, в прошлом Досиев, но, как известно, жизнь сложнее схем. Вот. Значит, он нам расскажет про несингулярные кривые, и там индекс с ними связанный. Ну вот, с удовольствием предоставляю Анару слово. Пожалуйста.
Ну, на английском вроде, да? Или как?
Ну да, лучше, конечно, по-английски.
Хорошо. Так, спасибо. Сейчас я шеринг сделаю. Ну, Алеш, вроде можно, да? Уже
да, уже можно.
Так. Посмотрим. Ну как, видно сейчас?
Ну да, прекрасно.
Ага.
Слайд presentation даже написано.
Ага, да. Вот еще annotation у меня здесь есть.
О.
Сейчас. А почему annotation? Вот он вышел сейчас. Sharing. Spotlights. Yes. Okay.
Okay.
Yeah, let me start. Yeah, hi everyone. It's a great pleasure for me to have a talk in the seminar and algebras in analysis. Well, I wish to talk about some sort of algebraic spectral theory. Thereafter, I'm going to switch to Fredholm sort of index concept within this algebraic spectral theory. Well, concerning algebraic spectral theory, it should be treated like a very algebraic version of all analyses. And apparently, it's just grotesque schemes. They can be treated like sort of analysis in a very, very algebraic case. So in contrast to our seminar, it's sort of analysis in algebras, not in opposite way, right? So you might not like it. Let me just warn about it. So as a basic tool, we're going to use, all stuff from commutative algebra, right? And trying to treating them again from our new point of view, that's actually is all about this spectral theory, right? Well, the crucial role, well, let me say the main moment is all about Noetherian modules. Noetherian stuff, probably some indirect analogues of the Banach spaces from the standard analyses. So we're going to use again this sort of eigenvalues, right? In general, the primes, prime ideals, and so on. Well, let me start slowly because it's a bit, it could generate some confusion of what it's all about. And I will try to, in every step, to explain what it's all about. So let me start with simple stuff. What is the spectrum? Yeah, so we're going to fix a field. And RK is just a commutative K algebra. Now we have a module. So the circular module turns out to be a K-vector space. Well, you can imagine sort of the space with the algebra of operators. So, we know what is the spectrum, right? In general, the set of those A where X minus A is not invertible over M. So it's sort of subset of this affine line. Well, this is just K, the field K, but equipped with the Zariski topology, right? They are zeros of the polynomial as a closed set. So in general, X minus A is a linear transformation from M to M. We can talk about this, the kernel, co-kernel, right? Just to indicate what has been invertibility, what has been spectral pooling. But spectrum can be empty set here. It's quite possible. For example, if you get this polynomial ring as a module of the fractional field, and X is in a multiplication operator, then spectrum will be just empty. But at the same time, spectrum can be all the line. This is also quite possible. Like, for example, in this case. Well, it's going to be an open, dense subset. Yes, for example, for this hyperbola. It's going to be open dense set. So in general, you may have some very exotic cases. And to contrast to our understanding of spectrum, is going to be like non-empty-camped set. But there is a case. Let me go up. Yeah, look at this case. It's something wrong with this one. Let me off. Okay, yeah, we're here. Now let's switch to that. So everyone knows what is an index, right, from the linear algebra. If you have a linear transformation, it's going to be difference of dimensions, right, kernel and co-kernel. Whenever both dimensions are finite. Well, if M is just R, the ring itself, so, well, we used to write like IX instead of IRX, right? So, you know, the every X is acting like a multiplication operator, so it makes sense to talk about the index, right? So we can again select the set of those where index is finite, right? It makes sense. So RIM, sort of. For example, the non-zero element of the field, the invertible elements, and they are also inside of this finite index case, right? And all of them inside of the non-zero elements of the ring. So overall index is a function like that, right? The z-valid function. Well, what we know from analysis, so the finite index class, the Fredholm operators, right? The index is a continuous function. Or certainly key moment here, like the set of all the invertible elements is an open set in operator algebra, right? That's not the case in general. For example, even for topological algebras, that's not true. So we shouldn't expect something like that in this theory. But what can be done? Let me explain just slowly. Well, and finally, let me mention about, so if M is a finite dimensional space, then the every index of every linear transformation is just 0, right? We know it. It's a standard linear algebra. Okay, look, that's a case when spectrum is non-empty. And by somehow we can calculate spectrum and index, both of them. So we're going to fix an algebraically closed field. R is an algebra-find extension. Well, algebra-find extension means just as the finitely generated algebra over K. And M is a Noetherian R module. So every submodule of M is a finitely generated R module. Right? So, well, you can imagine you have a vector space and a finite number of linear transformations, right? And this structure is a module structure, is generating a Noetherian R module structure. Suppose. In this case, spectrum is a non-empty set for every X. Well, we can calculate in this way. For example, this expansion is now like it's a known chain in commutative algebra, like Noetherian module has this sort of chain of submodules whose gaps, they are sort of R over some primes. Pi is a prime ideal. Well, let me recall again, the ideal is said to be a prime if this quotient is a domain without any zero divisors. Right? So associated primes, they're going to be inside of the set, and this set will be inside of support. Well, prime is called an associated prime if it's just annihilator of some non-zero element of M. Well, for example, if this associated prime is maximal and K is an algebraically closed field, then we can use, for example, Zariski, Milstein, and Stats. In this case, this ideal turns out to be like ideal generated by this generator minus some constants, right? So that exactly means this ideal representing is the eigenvector and eigenvalue. So in general, this stuff is a sort of representing eigenvalues here. Support is a sort of those primes such that the localization at every point is non-zero. The support in general represents spectrum of the module. Or, well, if you wish, you can say the joint spectrum, right? Anyway, this sort of stuff is well known. Routine, the commutative algebra book, you can see there. So using this chain, you can calculate the spectrum, like the spectrum of a union over all these gaps. So as a corollary, we can say that spectrum is either a finite set or it's a dense open subset of A1 in the Zariski topology. Well, you can accept it like sort of analog of spectral decomposition. So you have a chain of invariant subspaces. You can calculate spectrum over all the gaps, right? And as a result, you're getting this sort of the spectrum. All calculation of spectrum is you're reduced to calculation of spectrum over these domains. Well, the gaps again can be quite huge. So you may have just as a gap, like, for example, this guy is a domain, so spectrum of the multiplication operators can be all the field K. Well, but if length of the module is finite, then all the stuff looks like a very linear algebra, like associated primes, they're maximal ideals, they're the same. So M turns out to be a finite dimensional vector space, and every X is triangulizable like that, is a triangle structure. So you can choose a basis, right? Triangulation, so you have an eigenvalues here, and so on. Well, we know all this spectral understanding can be generalized for the tuples, right? So suppose we have some tuple R tuple in R, and M is R module, so we know what is in Kosul complex, right? We can generate this Kosul complex with the differentials, so we can generate the homology groups, right? This is a routine, right? Standard. Well, if we have finite dimensional homology groups, so then we can introduce sort of index of this family Y. This again is well known in analysis, for example, the sort of essential spectrum, right, and the related indices, right. And this guy is a sort of Taylor spectrum, the joint spectrum, for this tuple over the module M. Well, so first toward the projection property. So it's better to have sort of nice, satisfactory the spectral theorem with all spectral mapping theorems on. Well, this is a key technique. It's also well known in analysis for the joint spectral theorem over Banach spaces. But this one is an algebraic lemma, a sort of Bourbaki lemma. So how to use to drop, I mean, use sort of induction or just projection property downward, right? So you have an R tuple. This is R minus 1 tuple. So YR is acting over homology groups in a natural way. So then its kernel and co-kernel, they link to the piece homology group of the tuple Y. So this is crucial, right? So it's a technical lemma. It's immediately generates this sort of inclusion, right? Spectral property on the one side. So the projection of this to first R minus 1 coordinate is going to be inside of the spectrum of Y prime. Well, if index is finite, then so well, actually, it's better, right? Y prime is, yeah, if index is finite, then all the stuff is finite, so we can calculate in this way, right? For example, if index of the Y prime is finite, then all these homology groups, they're finite. So this is the indices, they're vanishing, so all the stuff is vanishing here. It's also one way how about the index function. So if it's finite for the less tuple, then adding up extra tuples, index is going to vanish automatically. So this sort of triangulation result. So when it's better have the finite index, it will be almost criteria, but almost. So let me say slowly, we're going to fix the algebraic closed field. Suppose this sort of extensions we have. And RK, the bigger one, is an algebra fine extension. And this gap is integral. So integral means that every element from here is a root of a monic polynomial with coefficients from R prime. So integrality is the analog of the case when the spectral theory is not changing, it remains invariant. Well, you know, in the analysis, we used to say like the complete subalgebras, when you're passing to subalgebras, spectrum should live invariant, right? So the analog here, they plays the role by integrality. So if this gap is integral, then the spectrum, they are the same. Dimensions, they are the same crude dimensions. Anyway, so we have the stuff is extending of R prime. RK is an algebra fine extension, and this gap is integral. Suppose M is a Noetherian R module of a bigger one, and we have the tuple. Well, actually, inside of R prime, it is generating a maximal ideal here in R prime. That's enough to make a conclusion like index will be finite. So in this case, the module structure of the homology group also nice. It's a triangulizable R module structure. Even R prime structure is diagonalizable. This sort of structure theorem, but the main part for us is all about the finite index, when we have a finite index. So that's the case. This tuple should generate a maximal ideal inside of some subalgebra. Well, this gap can be integral. It will be enough.
Well,
so for an ideal, this almost is telling like integral property will be almost equivalent. Like tuple generating A, this gap is integral. Then you're gonna find the tuple where index will be finite, and module structure will be nice, and the radical will be a finite intersection of maximal ideals. All the stuff they're equivalent. Well, finally, the projection property. So look, algebra fine extension, algebraic closed field, and Noetherian module. Then we have this nice projection property. In particular, every joint spectrum is non-empty. And index finite whenever this gap is integral. So that's a projection property.
да. Алло. Илюха, я на семинаре, потом отзвоню. Да? Ты дома, да?
Finally, the spectral mapping property.
Ох вы какие, ну ладно.
Again, the same conditions, like RK is an algebra fine extension of algebraically closed field, M is a Noetherian module. Then we have this spectral mapping property for all tuples X, PX from R. Yeah, that's all about this, the algebraic spectral theory, like what we need. Just I've just mentioned some details. What is that, right? How theory works. So this one is also a sort of confirmation, like the Noetherian stuff is a sort of indirect analog of Banach spaces, right? So there's a nice structure here when we can do almost everything like in analysis. Now let me turn toward the simple stuff like index of a single transformation. Well, first some terminology again. So if my module looks like that, quotient with respect to some ideal, and I have tuple here acting here, then we used to write IAY instead of this stuff. And module is said to be reduced if this stuff is reduced. This is an annihilator. Reduced means in this theory the nil radical is 0. Okay, so this sort of terminology. Now look, the first moment how we can calculate the index using again the same sort of chain of submodules in the Noetherian module. Again, fix an algebraic closed field, an algebra fine extension, and Noetherian R module. Well, we have again the same R tuple. This gap is integral. So this one only need for having a finite index. Then index can be calculated as this sum. Look, everything here, the minimal primes, the localizations, they turn out to be the finite. This is an index over R over P. This sort of multiplicities. And this part is a rest. Well, if M is reduced, so this multiplicities can be calculated directly like that. This is a fractional field. This is a dimension. There are famous multiplicities in algebraic geometry. I mean, there are scheme-theoretic multiplicities calculating sort of self-intersections, right? How many times they're crossing from the same point. Well, I will say about it. So this part is important for us for the future, when in the case of the curves. Anyway, this is the general result how we can calculate index throughout all this spectrum, like the primes. So module is said to be torsion-free if annihilator is 0. Right? So R is torsion-free means R is a domain, for example. Well, if it's not a torsion-free, as you know, this construction, so we can generate sort of submodule. Passed to a quotient is going to be a torsion-free. All right. So the first lemma is indicating, right, the link between the index over the ring itself and index over the module. Anyway, let me say, so we have a variety over the field with this coordinate ring R, and K is a fractional field. Y is an R tuple with a finite index. M Noetherian R module, then the calculation of the index over M can be calculated like this multiplication. Yeah, this result is true whenever the dimension is less or equal to 2. So this one, it's technical stuff. It needs more commutative algebra. So all these tricks, they work in the case when dimension is less or equal to 2. So the index of a ring divides the index of a module M. For example, whenever this guy is an irreducible algebraic curve, so curve dimension is 1, right? Okay, so the special case when we can use it as a module is going to be normalization of the module of the ring R in the finite field extension. Well, normalization is a special construction in this algebraic geometry. It stands for the nonsingular stuff. Whatever singular you have is going to be removed by passing a bigger stuff, like R prime normalization. For example, you can use the same formula here by passing to a normalization. The same formula, it works. Okay, now, before formulating the main result, we have to make a decision about this continuity I told you about the index. We know in general, we have a nice topology in the Fredholm theory, like operator topology. But here we have something else. So we can generate like a filtered topology in the following way. So you have a ring R and the maximal ideals. So let me define a support as a sort of non-negative function, non-negative non-trivial function, whose support is finite. So I can pick up some primes and get some powers here and look at this intersection. So intersection, find number of the powers of maximal ideals. So this guy is a non-zero when, for example, R is domain, right? And this stuff altogether generates sort of filtered topology. That's called the F topology, let's say. Well, when R is reduced, so nil radical is 0, right? Then this topology is Hausdorff. Well, you know, this is a Hilbert, Lustel, and Satz. So this nil radical and the Jacobson radical, they are the same, right? They coincide. So if it's 0, that means the intersection of all maximal ideals is going to be 0. So that's exactly that we need for the topology to be Hausdorff. So this stuff turns out to be a topological ring, right? With this filtered topology, and we can talk about this completion. Like the uniform space, we can talk about always the completions. So the completion turns out to be like that. It's a direct product with all these completions. So let me explain what is that. This guy is a Hausdorff completion with respect to p-adic topology. So this result is due to Bourbaki. You can see there, the community of algebra. They're proving there this sort of topology and getting this completion. Well, this notation actually can be justified, like if you look at this argument here, the problems that R of some power of P is a local K algebra, because the P itself is maximal. So, and no prime apart from P could contain P to the power, right? The prime avoidance, if you wish. So, well, there's actually local, so it's the same like as a localization. Then we can apply the localization functor. It looks like that. And eventually, it's a localization with respect to power of this maximal ideal. Right? So this guy RP is actually the M-adic completion of the localization. So this is from another point of view. This guy is actually a completion of the localization. Okay, so for an ideal, the following assertions are equivalent. So that's a case that we are looking for, right? Having a finite index. Dimension is finite. Length is finite. The ideal has a primary expansion. The maximal ideal of the course is going to be P1, PR, and every ideal is primary. So in this case, this ideal would contain some of this Bn, our neighborhoods of the 0. And dimension can be calculated like that. Sum over all this primary expansion. Well, here we are involving the famous result from Lasker-Noether, right, about the primary expansion. And we can prove that all the stuff be equivalent. So this sort of description of our topology, right, our filter base, what's happening here. Look, this is a result about the continuity of the index. Look, this sort of continuity makes sense. So we have a variety with a coordinate ring. Then this index, it turns out to be a continuous homomorphism. This is actually homomorphisms of abelian semigroups. So you know the famous property of index, right? Index of the multiplication is the sum of indices. But pay attention here about the topology in Z. It should be with left order topology. It's not discrete topology, right? Because the topology is a bit different. So left order, the case, for example, all the stuff is going to be a closed set for every n, right? So this sort of continuity makes sense. So index is a continuous stuff. Yeah, so I said about it, well, we cannot get the direct analogues of this Fredholm theory, like when Z is cubed with a discrete topology. Well, it's all related to the topology of R. It's quite a different topology, right? So, for example, the invertible elements, they may not be open. Okay, so we have continuous index. Now, let's switch to calculation of the index. How we can calculate and get some result. What is that? For example, we are looking for a case when we have a ring with every non-zero element has a finite index. For example, to classify all the stuff. Well, I need to mention something from the valuation, discrete valuation. What is that? So fix a field K by discrete valuation. We mean a surjective group homomorphism. So K star is a set of non-zero elements in the field. Well, with this sort of property. In Russian terminology, narmirovание.
How?
Narmirovание. Well, I will provide an example. What is that? It's a bit different stuff. The moment is that having this sort of discrete valuation, you can automatically generate a local domain. So non-negative elements here, they turn out to be a domain, and whose unique maximal ideal looks like that. V is strictly positive. So the zero valuation exactly represent the invertible elements. Well, it's going to be proved that it's a principal ideal domain, unique factorization domain. It has a very nice properties like regular local ring of dimension 1. And yeah, the K is a fractional field. Well, the regularity actually, it's again another quite deep theory, Krull's local theory, how to measure the dimensions. I mean, what is mean regularity here, regular local ring? Well, that's exactly the case when this sort of dimension is the same as a dimension of the ring A. So dimension here means actually the longest chain of the primes is just 1. So you have a 0 prime and this maximal and nothing else between them. Well, discrete valuation rings, basically they are representing the local ring of the non-singular variety. It's actually measuring non-singularity. Well, look, that's the case. How to prove that it's a principal ideal domain? So you have to choose elements, special elements whose valuation is 1. And then every x has a unique factorization. This guy is invertible. These are powers of n. So every ideal turns out to be principal like that. And this is the valuation means the minimum of all v of x. Well, now example, let's see what is that. For example, you can fix the field and look at this field of all formal Laurent series. So the formal Laurent series, they look like that. The powers of, they're sort of like a power series, psi n, but the powers can be negative, but it should be bounded from below, right? So it's a case when, yeah, so we can measure, for example, the order of vanishing of x, the least possible n where lambda n is non-zero. Anyway, the measuring this v turns out to be exactly valuation on k. So in this case, so this is our field. In this case, our ring, the local ring, turns out to be a ring of all formal power series with its unique maximal ideal generated by Xi. Well, actually, every valuation ring almost can be driven like that through the Laurent series. But look, that's a case when that's possible. If you want a DVR, discrete valuation ring, which contains its residue field, then is Newtonian local K algebra with maximal ideal. So by Kroll intersection of all powers is going to be 0. So we can generate the M-adic topology. And we can look at this completion. Completion turns out to be Newtonian local K algebra dimension 1. And we can use the Kohn structure theorem to prove that it's actually the algebra for formal power series. So this guy has a valuation, so we can reduce it back. And our initial valuation is actually the restriction of this valuation. So whatever discrete valuation ring you have, but it should contain its residue field, then you can complete it. And its completion turns out to be a formal power series where you have an evaluation, right? And then reduce it back, you're going to have V. Now, this is a famous construction, how to get the V. Well, look, that is the famous result probably due to Serre. A is a discrete valuation ring, is a normal domain of dimension 1, normal domain of depth 1, regular local ring of dimension 1, and M is a principle of height at least 1. So the key moment here that this turns out to be normal. So that's exactly describing the local behavior. I mean, non-singularity at fixed point of an algebraic variety. So what has been Dedekind? Dedekind Newtonian normal domain of dimension 1 is called the Dedekind domain. So all the principal ideal, a ring of algebraic integers, all of them, they are Dedekind. So Dedekind is a sort of, well, local Dedekind exactly means DVR, discrete valuation ring. So actually it's R is Dedekind if and only if every localization at point P is DVR. Dedekind domain, they possess very, very nice property, like every ideal admits as a unique factorization over all primes. Look, you're getting the prime, getting this, the valuation of this ideal at P, and get it power, and you're going to have this sort of unique factorization. So in Dedekind, we have this sort of expansion, unique factorization. This is important for us. Look, we can measure the multiplicity function in a Dedekind domain. Having a Dedekind, so I can add up all these powers, all these multiplicities, and add them up. This guy is a special function. Well, I can define as a function of R because I can get this element and generate the principal ideal. And look, this function possesses the property which is very similar to index property for all ideals. Look, R is defined over Z like that. R of, I mean, rho of the principal ideal. Again, this guy turns out to be again continuous, but with respect to right order topology. In this case, this interval is closed by every end. So this sort of multiplicity function of R star. Okay, now I'm very close to formulate my main results. So let's have an algebra finite with X as a tuple. And suppose R is a domain of dimension 1. Well, that's exactly representing the coordinate ring of the reducible algebraic curve. So the spec looks like that. This is my algebraic curve, and this is a generic point. It's a zero ideal. Well, if R is Dedekind, we used to say it's a Dedekind extension, right? So if this coordinate ring is Dedekind, that's exactly it stands for the non-singular reducible affine curves. Yeah, look, in the case of the Dedekind, so dimension of every quotient with respect to non-zero ideal, well, in general, R is an infinite dimensional space. If you look at our as a vector space of our case, infinite dimensional, but the quotient with respect to every ideal turns out to be finite. And in this case, we have a link to our topology, to filter topology. And multiplicity is just the sum over all the powers of the BM, right? So BM is a factorization over all primes, and you have enough multiplicities. If you add them up, it's going to be exactly rho. Okay, look, this is our main result. So look at the case when index of every non-zero element is finite. Let's say, in this case, Rk is an I variety. So in this case, index of every tuple will be finite. Well, actually, it's going to be 0 if R more than 1. So get a fine variety of algebraic closed field with its coordinate ring R. Then is an I variety if and only if Y is an irreducible curve over K. Well, but calculation of the index is a bit complicated in the sense that if you wish to calculate the index precisely, you have to use the raw multiplicity function of the normalizations. You have to pass through the normalization of R and K. Well, the normalization turns out to be a Dedekind. It has a raw, so you can draw it back and put the minus is going to be your index I. Well, that's an index over R, but you can extend. I told about it, so we can extend index over any module, right? It's going to be like multiplication. It's a multiple of the index with this sort of number. Dimension K, it's the extension, right? It's a sort of filled extension. And our index turns out to be continuous with respect to left order topology. Now, from practical point of view, how are you going to use it, for example? You can choose any vector space, fix a linear transformation, single linear transformation. And single linear transformation defines the KX module structure, right? In a natural way. So we suppose that this structure is Noetherian. So if you get polynomial, its degree divides our index. This is the index of the linear transformation. Well, what's the meaning of that from point of view geometry? Let me explain about the special elliptic curve. So look at this elliptic curve. And in this case, we can calculate the index. For example, we have an action X and Y. It's not so hard to calculate index directly. Just so pass to a quotient generated by ideal X, and then this quotient turns out to be a fine dimensional space, and calculate its dimension is not so hard. Well, what they are actually, so what kind of geometry stands behind, let me explain. So in general, we had a coordinate ring R, right, of a variety Y. So in our case, variety is a curve. So if you fix an element from here, f, it's in general a polynomial in, was actually the equivalence class of the polynomial in n variables. So this polynomial defines actually a sort of hypersurface. Defines hypersurface. Well, this curve, the passing through this hypersurface, they have an intersection, non-trivial intersection. So our result is stating that the index of this transformation f in the coordinate ring R, exactly calculating this intersections up to their multiplicities. So you know the curve could cross twice from the same point, go like that. Well, certainly this sort of multiplicity here, it has a bit scheme-theoretic multiplicity. But in the routine geometry is exactly the number of self-intersection, the crossing from the same point. So calculating these numbers is going to be exactly my index, but with the sign minus. So look at this example here. Index of x turns out to be -2. Let me show you here. Well, you can calculate the same index for y. It turns out to be -3. Well, what they are indeed, look at this example. Let me show you now. I need to rub out all the stuff here. Okay. Look, this is my elliptic curve. I have written to the computer like just y squared equals x cubed minus x. So look, we calculate x and y. So index of y exactly shows me the x line intersection, exactly they are free. Look, that's exactly free there. But the other index of x, well, index x means that when x is 0, right? So it actually shows me the y-axis. So if you try to calculate this one, we have seen -2. So 2 exactly the multiplicity here, because when you plug in here x is 0, it's going to be just y squared is 0. So look, that's multiplicity pops up here. Exactly shows you -2. All right. Well, thereafter you can calculate the index, for example, using the properties of the index. You can calculate the powers of x to the s, y to the t, right? So it's just using the scheme theoretical version of the Bezout theorem. So exactly Bezout, this calculating number, is telling you that this number, sum of all multiplicities, is actually the multiplication of the degree of variety and degree of this hypersurface. So as a result, we are getting like the index actually is just multiplication of the degrees. So, but degree of the hypersurface in the previous example, that was the degree of this polynomial actually. So that's why it shows me degree divides my index, right? So it's a consequence of the Bezout theorem, right? Yeah, anyway, look, that's a case how we can calculate index. In this particular case, well, certainly this sort of result can be generalized with a higher dimensions, but I don't know what's precisely what we have to do there. Yeah, let me stop here. Okay, that's all my talk. Thanks for listening.
Oh, so you have finished?
Yes, yes.
Well, your lecture was indeed very strenuous, so maybe it is even good that because it was not so easy to follow you, but it was very interesting, yes, and impressive. So thank you very much for an excellent talk. And now, gentlemen, I think we must say each other goodbye and resume our seminar in the next semester. Usually in Soviet time, somewhere in the beginning of summer, there was, I don't know why, there was information that Iranian Medjlis went to holidays. So it was considered as very important information, so we knew. So now our Medjlis is going for winter holidays, and let us resume our occupation. Well, it will be, no, you know that official time to beginning of the spring semester is 7th of February. So somewhere maybe a week later we shall resume it, etc. But everybody, of course, will be informed about it. And now thank you very much for, first of all, for our speaker, for our this speaker and others also, and for everybody who spent his time to come virtually, to come here and to listen us. Yes, so thank you very much again, and we shall meet you, I hope. And now I must also wish everybody good health because of, you know, this specific time when we live now. Yes, let's be careful, be with masks, etc., etc. Yes. So goodbye again. Thank you very much. Yes.
До свидания.
До свидания. Yes.